All right, let's talk about TensorFlow, because I'm willing to bet it's way bigger, way smaller, and a whole lot more interesting than you might think. We're going to go on a journey across a mind-boggling range of scales today, so let's just dive right in.
So when you hear TensorFlow, what pops into your head? Probably training a neural net on your laptop, right? Or maybe on a powerful workstation with a nice beefy GPU. And yeah, you're not wrong. But that's really just the tip of the iceberg. It's only the very beginning of the story.
Because get this, the very same ecosystem that powers machine learning in these giant globe-spanning server farms is also designed to run on tiny battery-powered sensors. I mean, some of them are smaller than a grain of rice. It's wild. We're going from the absolute macro to the absolute micro, and we're going to see exactly how TensorFlow pulls it all off.
Let's start at the top. The biggest AI models out there today are just colossal. We're talking hundreds of billions of parameters. You simply cannot train them on a single machine. I don't care how powerful it is, it's just not going to happen. And that, right there, is the challenge of big AI.
So what's TensorFlow's answer to this massive problem? It's something called TF Distribute Strategy. At its core, it's an API that's designed to do one thing: spread the workload. You can think of it like this. Your model is the star player, and instead of training alone, you're giving it a whole team of processors to train with, all working together in perfect sync. The whole idea is to make this incredibly complex process feel simple for you, the developer.
And the cool thing is, it's not a one-size-fits-all solution. Nope. TensorFlow gives you a whole menu of these strategies, and you just pick the one that fits your hardware. So, if you've got one big machine with a bunch of GPUs, you'll use mirrored strategy. If you're lucky enough to be using Google's super specialized tensor processing units, well, there's TPU strategy for that. And if you have a whole cluster of machines, multi-worker mirrored strategy is your friend. It just goes to show how flexible the system is. There's a tool for pretty much any large-scale setup you can dream up.
Okay, so you're probably thinking, coordinating all that hardware must be a total nightmare of code, right? But here's the real magic. When you use Keras, it is shockingly straightforward. Seriously, you just pick your strategy, you open up what's called a strategy scope, and then you define your model, your optimizer, all that good stuff right inside it. And that's it. With just a few lines of code, you've told TensorFlow exactly how to distribute your training. It's incredible.
Okay, so we've scaled our computing power up to massive levels. Now, let's switch gears and scale our thinking in a totally different direction. We're going to move from the physical scale of hardware to, well, the conceptual scale of uncertainty. Think about it. A standard machine learning model gives you a single, confident answer. It tells you this image is a cat. But what if it's a really blurry picture of a cat? Or maybe it kind of looks like a small dog. How confident should you really be in that single prediction?
And this is exactly where probabilistic modeling completely changes the game. Instead of just giving you one answer, a probabilistic model gives you a whole distribution of possible answers. It doesn't just say it's a cat. It says, you know, I'm about 85% sure this is a cat, but there's a 10% chance it could be a dog. Being able to quantify that uncertainty is absolutely critical for making reliable, smart decisions in the real world.
And TensorFlow's tool for this is, you guessed it, TensorFlow Probability, or TFP for short. It's a library built right on top of TensorFlow that basically combines the raw power of deep learning with the principles of statistical analysis. It lets you build models that don't just predict, they also understand and tell you about their own uncertainty.
TFP is structured in these really logical layers, building from the ground up. At the very bottom, you've got the fundamental building blocks of statistics, things like probability distributions. Then, you build on top of that with tools for actually constructing your model. And at the very highest level, you have these incredibly powerful algorithms for inference, which is really just how the model learns from data. It gives you a complete toolkit for probabilistic machine learning.
All right, so we've gone from massive clusters to the abstract world of probability. Now I want you to make a hard pivot with me, all the way to the other extreme of the physical world, the absolute tiniest scale where machine learning can possibly operate. Just take a look at this number. There are over 250 times billion microcontrollers out there in the world right now. They're in your car, your microwave, your thermostat, they're in everything. This is the world of TinyML, and it represents a colossal opportunity to embed intelligence into all the everyday objects around us. But there is a huge catch. These devices are incredibly constrained. As the researchers behind TensorFlow Lite Micro put it, they're missing things we take for granted every day, like operating systems or dynamic memory. Sometimes they don't even have standard floating point hardware. We're talking about working with just a few kilobytes of memory. It's a completely different universe. The solution is TensorFlow Lite Micro.
This isn't just a shrunken-down version of TensorFlow. It was engineered from the ground up, specifically to handle these severe constraints. It's designed to be portable, flexible, and most importantly, incredibly small and ridiculously efficient.
So how do they pull this off? Well, TFLM uses an interpreter, which you might think would be slow. But here's the really clever part. Most of the heavy computation in a neural network happens in just a few highly optimized functions. This means the interpreter's own overhead is tiny. For a complex vision model, it's less than 0.1%. This design creates a framework that's super flexible without sacrificing performance where it really can.
So, we've gone on quite the tour. We've journeyed from server farms that fill entire rooms through the conceptual space of uncertainty and all the way down to processors that are barely visible to the naked eye. Let's tie it all together.
What this all proves is that TensorFlow isn't just a single library. It's a complete, comprehensive ecosystem that's designed to scale in every single direction. Whether you need massive computational power, sophisticated probabilistic reasoning, or intelligence on a tiny, power-sipping chip, the TensorFlow universe has a tool designed specifically for that job.
And that leaves us with one final thought. We've seen that machine learning is no longer confined to the data center. It can run on the network's edge, it can run on your phone, and now it can run on the simplest and most common devices we have. So if intelligence can truly fit anywhere, what becomes possible? What problem are we going to solve next?